reflection. Now, this guy named Williford Snell, we were talking about refraction, and we talked about how these two angles are not equal to each other. We could see that, right? And there was a guy named Williford Snell who also knew that, and he did the experimentation to determine the relationship between the angle of incidence and the angle of refraction. We call it Snell's law in his honor, or also the law of refraction. And it's this: N1 sine theta I, which equals N2 sine theta R. This is equation number 50 in your equation chart. The hardest part about this equation is not really the trigonometry, even though some of you may be scared of that. The hardest part is figuring out where everything goes. And so these are the variables for this equation. And I'm going to start with N2, and you might want to make a note of this. N2 is where I would start with every problem involving Snell's law. And the reason is because N2 is the easiest to remember, because N2 is the index of refraction of the medium light is traveling into. Did you hear that? N2 is what you're going into. So it's easy to remember what N2 is. In the example I just showed you, from water going from air into water, the N of water would be the N2, because that's what we're going into. How many times can I say N2 in 10 seconds? N1, therefore, would be the index of refraction of the medium light is traveling from. And then we've already discussed this, but theta I is the angle of incidence, theta R is the angle of refraction. Don't forget that we always measure these angles between the ray of light and the normal line. So this is Snell's law. So let's look at a Snell's law calculation. Light strikes water where N is 1.33 from air at an angle of 36 degrees to the normal. What is the angle of refraction? If I were you on all these problems, and this is no different, the first thing I would do is draw a picture of what's going on, and this is a good picture to draw right here, but don't make it take up all of your workspace, because you're going to need some space to work. Alright, so this is something like the picture you should have drawn, going from air into water, and this problem says that N of water is 1.33, and it tells us that it's striking that water at an angle of 36 degrees to the normal. So you should be able to tell that this angle right here is 36 degrees, also because they're asking you for the angle of refraction. So anytime you have a refraction problem that involves angles, you should know you're going to deal with Snell's law. So that's N1 sine theta I equals N2 sine theta R. And again, as I said before, the hardest part is knowing where everything goes. You always start with N2 and ask yourself, what is light going into? In this case, it's going from air into water. So N for water is actually our N2. So N2 is 1.33. N1 is what we're coming from. That's air, and the N of air is 1. That's something we need to memorize. And now we put everything else in. We decided that the angle of incidence was 36 degrees, so sine 36, and then we have sine theta R over here. Now don't forget, this is just a number, and this is just a number if we had the angle. So what we need to do first is divide by 1.33 to do this. If you do sine 36 in your calculator and then hit enter, and then divide by 1.33, you will get 0.4419, right? Now, really important at this point that you realize that this is not your answer. It's not the answer. This is the sine of the angle that we want. It's not the angle itself, right? Be careful if you get a decimal. That's probably not the angle that you want. You might want to make a note of this to yourself. Anytime you're looking for an angle, you're going to have to do the inverse sine function, which is second sine in your calculator. So we need the angle. We're going to do the inverse sine of this number that we got here. The inverse sine of 0.4419. Really important that you keep a lot of decimal places here. I recommend at least 4. Inverse sine of that number is about 26.2 degrees. This is our answer. So notice that the light bent. We came in at 36 degrees, and it bends about 10 degrees, came out at 26 degrees. And this is probably more dramatic than what we have going on there, but it's a decent representation. So that's how you work with Snell's law. Now, to move us into the next part of notes, I just want to perform a thought experiment with you. This thought experiment, let's imagine we have water and we have air. Let's say for whatever reason, you're under the water and you're going to shine a laser out of the water into the air, right? And so here's our normal line, and you shine this laser from the water out into the air. And so my question is, what happens to the speed of the light as it goes from water into air? Well, air is less optically dense, so the light will speed up and it bends away from the normal, which, by the way, let's go ahead and stop right here and go back for a minute. At the very beginning of the first video, we had the light going through a block, and we knew the light bent to the left as it came in, and then it bent back to the right as it came out. And the reason is because as it came into the block, the light slowed down, therefore bent toward the normal. When it came out of the block, the light sped up and therefore bent away from the normal. And it's interesting that actually these two lines, even though I didn't draw them that way, actually end up being parallel. Anyway, back to our hypothetical, our thought experiment. This is what happens to the laser. It refracts in this way, and the people out here can see it. Now, the thought experiment is the question, what happens to this laser if instead of shining at this angle, what if we shine at this angle? What if we move the laser that way? Well, hopefully you can figure out that our theta r is going to increase because it can't stay here. It can't stay. This is now a straight line, and that can't happen. It can't move this way because if theta r decreased and the ray moved this way, that means that it would be bending toward the normal, and that can't happen when the light speeds up. And so our new ray would do something like this, right? And the thought experiment can continue that as we move this incoming ray more and more this way, that the angle of refraction continues to increase, and this new angle gets more and more crazy, shall we say. And I have some proof for that. Here's a block that has a circular edge to it, and I'm going to shine a laser through it. I want you to watch what happens as I make the angle more drastic. Notice as I increase that angle of incidence, the angle of refraction gets more and more and more extreme. And then our thought experiment comes to a close because, well, it doesn't come to a close completely, but I hope that you'll ask the next question, which is this: what happens, or rather, when, at what point does this angle, at what point does the light actually go straight along the water surface or the plastic or whatever else you talk about? At what point, at what angle can I produce a 90-degree angle of refraction? And that is possible to do. You saw that in the example with the block before. And when I do that, the angle is no longer called the angle of incidence, it's called the critical angle. Because as light emerges from a more optically dense medium to a less optically dense medium, it actually slows or speeds up rather, as we saw from the water going into the air. By the way, this whole critical angle thing only happens from a slow medium into a fast medium. And when it does that, it bends away from the normal. And so the critical angle, therefore, is the angle of incidence when this happens that produces a 90-degree angle of refraction. And you want to draw a picture of what's going on there in your notes, and to draw it, you need to draw something that looks like this. The angle, the light coming in, and it's coming out of the water at such an angle that the refracted angle is 90 degrees. It goes straight along the surface of the water or diamond or whatever else we're coming out of. And this down here is called theta C instead of theta I, critical angle instead of incident angle, because we're talking about critical angle now. Now, you need to mathematically be able to figure out what this is, and it's not that hard to do. We got to start with Snell's law. Now, as you move through your notes, there is a box there that says, therefore, don't put anything in the box until you see something here that's in a box. So we start out with Snell's law, which looks kind of like this. we change theta I to theta C, and we change sine theta R to sine 90, because that's what we want to get. Well, if you put sine 90 in your calculator, you get 1. So since sine 90 is 1, basically we can do away with all of this completely. So we can do away with sine 90. So we get n1 sine theta C equals n2. And all we have to do is divide by n1 on both sides, and we get this. And this is what you put in that box. This is equation number 49 on your chart. It's the equation to find the critical angle. And remember that N2 is the medium that you're going into, and N1 is the medium that you're coming from. Now, this is the equation that's in your chart, but mathematically, operationally, you're going to do something just slightly different. And if I were you, I would write that operational equation somewhere close to where you're writing this. What you'll do operationally is you'll do this N2 over N1 equation, but that only gives you the sine of the angle, and you don't want the sine of the angle, you want the angle itself. And so what you'll have to do is take the inverse sine of whatever you get there. So I would write this as an operational equation next to where you're writing that the critical angle is the inverse sine of the N2 over N1 equation. Now realize with this fraction, you might want to write a note to yourself. This only works if you're going into a medium in which light moves faster. And so for that reason, N2 will always be lower than N1, and if N2 is lower than N1, then whatever you get out of this fraction will always be less than 1. It will always be less than 1. Alright, so let's calculate the critical angle real quick. It's pretty simple. What's the critical angle for light emerging from a diamond into air? So we start with this equation. Remember, we're going to and from here. I'm going to have to solve this on in that case, light was moving in or from. This was actually not water. This was a diamond, and it said that the N was 2.42. This is what we're coming from, so this actually is N1. N2 will be air. So our equation here, when we put numbers in, becomes 1 over 2.42. Right? And we're going to take the inverse sine of what we get from that. All right? If you do that, you get 0.4132 here, and then if you take the inverse sine of that angle, you will get 24.4 degrees. 24.4 degrees happens to be the critical angle for diamond. Now, I want you to understand 24.4 degrees is not a very big angle. That's about this angle right here that we drew first. That means when you shine light out of a diamond at 24.4 degrees, it will refract directly along the surface, which means if we continue our thought experiment, if we continue to increase this angle, you can't refract any more than this. And what we get next is called total internal reflection, which means if we do this, we actually don't refract anymore. Now we're obeying the law of reflection, and the light will come back into the diamond. It will reflect off of the surface between those two, and we get total internal reflection. The total internal reflection occurs when the light ray strikes the surface at an angle greater than the critical angle. Again, this only happens if you go from a slow medium into a faster medium. It doesn't work the other way around. And the best example of this is fiber optics. And there's a video underneath this one to show you exactly how fiber optics work. This is the last thing I'll show you about total internal reflection. Let's start again with our refraction. Notice we had our refracted angle here. Refracted angle increases, and at some point we get to a critical angle where we're going directly along the surface. And then you'll notice we're actually getting some reflection the whole time internally, but now if we exceed that angle, I'm now getting total internal reflection. If you look over here, I get none of the light coming out on the other side, not in laser form at least. The laser light isn't coming out on that side. It's reflecting completely internally inside the block. So we get total internal reflection inside of this block. And then if I come back the other way, notice we get refraction again. It comes out. So that's total internal reflection.